Okay, good morning. Let's get started. Sorry, my computer sometimes just kind of get froze, and I had to force restart, shut down, restart. Okay, let's continue on the model construction in here. Okay, in the previous lecture we said to model a system, you need to have certain principles, okay, to stick to. There are many physical principles you can use. And in this lecture, I'll use a mechanical one and an electrical one to illustrate. For mechanical one, the most common one, as I show you, is the Newton's second law, right? For electrical, you have a KCL and a KVL laws. Okay. Now, for individual component, you also have the governing equations, and that's actually what you will use in combination with the physical principle to construct a mathematical model for a system. Okay. So let's take a look at for individual component, what are the governing equations? Okay. So let's take a look at first, very simple one. If you have an electrical resistor, you have a voltage across the resistor, then you have your current and the voltage, right, related by this simple equation right here. And if you have a capacitor, and the current going through the capacitor to here, the governing equation for the capacitor component is you have the total basically charge over the voltage V. Okay, you get the capacitance of this capacitor. Similarly, there's also basically the current is related to the rate of change of the charge with respect to the time. Okay, and if you substitute the Q into this equation, then you get the relationship between the voltage and the current, okay, for a capacitor. So I equal to C times dV over dt. And often sometimes you can also write it the other way. So basically 1 over C and I dt integration. Okay. So that's capacitor, right? And also there's inductor, indicating using L. You have a current I flowing through it, the voltage V across the inductor. Very similarly, your V is equal to L di over dt. Okay. So that's electrical. If you have a simple electrical circuit, analog circuit, and then those are the governing equation for each one of the components of the circuit. And then you can use, for example, KCL and KVL to combine all of the governing equations together, right, using the physical principle. That's electrical. So now let's take a look at a few mechanical components. So let's first take a look at a mechanical spring. Spring is a very common mechanical component. You see that in many different applications. Okay. I'll use this symbol here to represent a spring. And for spring, you can have a spring stiffness, okay, called K. So that's a small k to represent its spring stiffness. Okay, so when you have a spring like this, and in this case, okay, we'll show you a different case. One end is fixed, the other end is free. Okay, so this is called fixed end, and this is a free end. Okay. Free end basically means if you pull it out or press it, okay, then this free end will start to vibrate, right? Yeah. So we denote this end at here, okay, using an X. So this X at here represents the displacement of this free end at here. Now, when you talk about the displacement, okay, there needs to be always a reference. So you're saying displacement reference to somewhere, right? So in this case, that displacement x is in reference to the equilibrium location or position. Okay, so displacing the end from its equilibrium position. Okay, that's very important. Always remember, especially when you model something, right? There's always a reference to what location. There's also a different reference which I'll talk about. There's another reference is which direction you define as a positive, right? So in this case, we draw the arrow this way. So we're basically saying that direction, okay, is considered as a positive direction. Okay, so when the free end is moving to that direction, okay, in this case to that direction, okay, then it's the positive value. If you're moving, let's say 2 meters, that's too much, 2 centimeters to that direction, that's called positive 2 centimeters. Okay, if the equilibrium is here, right? But if actually moving to this way, right, then it's negative, basically. Okay. So arrow, so direction of arrow is the positive, okay, direction. Okay. So remember now, you have two different references. One is you define the variable reference to an equilibrium location. And you also defined a positive direction, which is a reference, another reference information for this variable x. Okay? Yeah. And now we apply our physical component equation. For spring, you basically use the Hooke's law. Okay. And Hooke's law says when you have a spring, okay, and then you elongate or compress it by amount of x, okay, then there will be an equivalent amount of force which equal to k times x. But this force, okay, is in the opposite direction of this displacement x. Okay, so this is the Hooke's law at here. F equal to negative. So this negative sign is very important. Okay, it's not just the whole magnitude of this force. Negative spring stiffness times x. So this F at here is called, okay, restoring force. Okay, restoring force, okay, and it is in the opposite direction, okay, of the displacement. Okay, so I want you to visualize if you have a spring and you initially it's at equilibrium, then you drag this free end, okay, you're elongating it, okay? Yeah. So the x goes this way, right? So the force go which way? To the opposite direction, okay? To the x direction, okay? That's what this negative sign means. If initially equilibrium and you press it, right? So now the x is actually, if you go this way, the x is, according to our definition, the x is considered as what value? It's a positive or negative? Negative, right? But because you're pressing it, the force still in the opposite direction of the x, the force will go to that direction, right? So even though you have a negative sign, negative, the force will become a positive force, okay? Yeah. So that's basically what Cooke's law is. Okay. And this is actually the simple case. One end is fixed, the other end is free. So now let's look at a slightly different one here. I have a spring, but both ends are free. Okay, so both ends are free. So in this case, how do we describe the governing equation for this type of spring then, right? Now because both ends are free, we can do the same thing. For this end, I'll define it as x1. And for this end, I'll define it as x2. Right? Because both ends can move. So I need to define two different displacement variables for this spring. Okay. So, and one end is defined as x1 and the other end defined as x2. Now you might wonder, why do you define two different ones? Can you define just one x1 for both ends? Unfortunately, you can't, because both ends could move at a different fashion, right? So you have to use two different variables to describe the displacement for each end. Okay. Very similarly, the way that we draw it here, the way that we define it here, right? So this x1 and x2, okay, they are the displacement, okay, with respect to equilibrium. Okay, respect to the equilibrium position or location. So equilibrium basically means you have when the spring is standing still, you have your one end is here, one end is here, right? Yeah. And now maybe this end start to move x1, this end start to move x2. Okay, that's what reference to equilibrium means. Okay. And also, right, you have two arrow signs at here, right? So the same thing, the directions of arrows, okay, the direction of arrow represent the positive direction of motion, okay? The positive direction of displacement. Okay, so again, two different references, right? One is reference to the equilibrium, the other is the reference of the direction, positive direction. Okay. So now let's apply the Hooke's law to this situation at here. Okay. Number one, okay, because the difference is both ends are free to go. So this time you're going to have to differentiate which end are we looking at. Okay? So for the first one, let's say if we have, an object attached to the right side, okay, to the right side of here, then let's think about what will be the restoring force, okay, to any object, okay, on the right. Okay, what will be the restoring force to any objects attached to the right free end? What is the right? Yeah, this is the right here, right? Yeah. Okay. Hooke's law says this: you have a total force, that's the restoring force. Restoring force equal to the spring stiffness times the net change of the spring length. Okay? Yeah. And it also you have to maintain that this restoring force will be in the opposite direction of this x1. Right? That's what the gist of the restoring force here, right? If you look at this first one here, this restoring force is in the opposite direction of the x, which is the free end. So in this case, this restoring force on this end needs to be in the opposite direction of x1. And at the same time, it has to be the net change of the spring length. So put a negative sign at it here. Right, that's the restoring force for an object attached to the right side of the end. See, you see the meaning here, right? So this one represents the net change. And this negative sign represents the force is to the opposite direction of x1. Okay. So that's what we call the governing equation for this component, right? For this end and here. So similarly, if we see what will be the restoring force to any object or basically a mass on the left. So the F will equal to negative k times 1 minus what? Exactly. Okay. We'll put these things together. If I have a mass, okay, somewhere here or somewhere here, and we want to derive the equation of motion, basically that's what we call model construction for example, this object or this object. Okay? And we will be able to draw a free body diagram, we'll be able to apply the Newton's second law, we'll be able to draw basically all the forces on these objects, right? Yeah. And one of the force for the green or the red will come from here or here. Okay? Good. So I'll give you a quick example right here, okay? Very quick example. So let's say we have a point mass, okay? Object with a mass m connected to the right end. Okay. If this is the only situation, okay, this is the only situation here, okay? Nothing else. There's no other external force, okay, on this object. So what do? If we need to construct a model for this object m and here, so we take, when you construct a model, basically what's the free body diagram? You isolate that object first, right? You isolate it, and then you sketch all of the external force onto this object. And in this case, there's no other external force except the force coming from the spring. And as we just learned, because this is attached to the right end, so the force applying to this point mass is pointing to the opposite direction of x1, and the value of this one here is what? Is k times x1 minus x2. So did you see any difference for now? The minus I got rid of, right? But why did I get rid of the minus? That's right, because I draw the arrow to which direction? To the opposite direction of x1. Okay? Yeah. So the magnitude of this restoring force is this much. And it points to the opposite direction of x1. Okay? Yeah. This is basically the free body diagram for this point mass. And that's it. Okay? Yeah. I will post maybe a video that I made quite many years ago. I think it's still valid. Basically, to have a little bit more in-depth, okay, into the details of the situation at here. So all we are talking about right now, okay, everything is general, right? General basically means I don't consider the actual location, the actual motion, right, where exactly it is, or how much the spring has elongated or being compressed. So we're not considering that at all, right? We're considering general. The general governs all of the basically specific cases. This is what we call it. The general governs all the specific cases. Now, one of the common thinking at this stage is always, is that the actual direction of motion, or is that the actual direction of the force, right? That is a very common thinking for now as you're learning new things. The answer is no. So this is not the actual. Actual means what? It means when I draw an arrow, you might consider, oh, this must be moving this way, right? When I draw a force pointing this way, and you must be wondering, that force must be pointing that way, right? But that's not the actual. When you plug in actual value x1, x2, that actual value may be actually pointing that way, right? But this governing equation will be able to deal with that, will be able to include that specific case. So this is basically a lot of time at this stage, we tend to always think from a concrete value, concrete example, right? But in this case here, you have to get used to, this is the general governing equation, right? Because you're deriving a general equation. What's the difference between this general and a specific value, a specific situation? Okay. So you can try, if you have an object attached to this direction, this side here, and what will be the free body diagram, and what would that force pointing to for a mass in this direction, in this side here? Okay. Any questions? Very good. Okay, so that's mechanical spring, and then let's look at another mechanical component called damper. Okay, mechanical damper. We represent a damper using this symbol at here. Okay, so I'll draw this a little bit precisely, because it's like a piston. Okay, so you have one shorter arrow, and then you have a barrel-like kind of things, okay, surround this shorter arrow. So essentially, it's like a piston that can move inside a cylinder, right? And this is called a mechanical damper. We use small b, okay, to represent this damper. This b here is called damping constant. Okay, damping constant, or damping coefficient. And more precisely, we call it the viscous damping. Okay, viscous damping. And if you observe many of the doors, okay, in university or even the doors, not necessarily doors at home, many of the doors, commercial gateway, okay, if you look at the hinge, right, I'm not sure this one has one. If you look at the hinge, there is basically sort of like a piston and a bar, right, inside the piston. So that's basically an example of a damper. Okay, so when you open it, okay, and you let it go, it doesn't close right away, right? So it closes slowly. That component provides a damping function. Okay, so that's essentially an idea of the mechanical damper. Okay. And for this case, I have one end fixed and one end free. Okay. Viscous damping basically means when you learn fluid, you will see some of the fluid, okay, some of the fluid has internal resistance to motion. If you look at syrup or oil, right, they're really thick, so they're not so easily to move or to flow like water. Okay? So that's basically, so there's sort of an internal friction in it. And this viscous fluid essentially is a fluid which does not flow easily. And viscous damping is a measure of the fluid resistance to the motion. Okay? Yeah. So if I have one end free, one end fixed, okay, and then you denote the displacement of free end as x with the reference direction, okay, drawn by the arrow. The governing equation, okay, for this damper is F equal to negative B times x dot. So basically the force is proportional to x dot, here represent velocity. So F is proportional to the velocity of the motion. Like the spring, right, force is proportional to the displacement and is proportional to the velocity. However, right, the F is in the opposite direction of velocity. Okay? Yeah. That's the governing equation for mechanical damper when one end is fixed, one end is free. So what if I have a damper that's actually both ends are free? Okay, so both ends are free, then you have x1 and x2, just like the spring, right? Define x1, x2 as a displacement reference to equilibrium first, and draw the arrows reference to the positive direction. Okay? And now, very much like the spring, you could attach an object to this side, you could attach an object on the other side. So on the right, if you have an object on the right, okay, if you have an object on the right, then there's going to be a restoring force, okay, applied to this object. The restoring force governing equation is F equal to negative B times x1 dot minus x2 dot, which basically means the restoring force is in the opposite direction of x1. That's what this negative means. Okay. And it also has it's proportional to the difference of the velocities at the both ends. Okay. So if you have the red object set here, the M, then according to the governing equation, you should have a force pointing to the opposite direction of x1 dot. Okay, so B times x1 dot minus x2 dot. So this time, because I already have the arrow pointing to the opposite direction of x1, then I don't need the negative sign at here. Okay? Yeah. Any questions so far? All good? Excellent. So now let's put things together. Okay? Let's take a look at some very simple examples of constructing a model. So let's start from electrical example. Okay, so you have learning. You must be learning this in 255 right now, I believe, right? You probably learned a little bit in 178. Not sure. But if you have this is called RC circuit. Okay. Here's the RC circuit. Okay. And we want to model this RC circuit. So the RC circuit here has input voltage source and you take the output, which is across the capacitor. Okay? So the idea is you inject this circuit with a certain voltage right here, this is essentially what we call, it's a known value, right? You can give it a sinusoidal here, you can give it a unit step at here, okay? Depends on the function generator. Then you use an oscilloscope, you measure the voltage across the capacitor, right? So you observe the response of the system, okay? So essentially this is your input, this is your output. Okay. Now, what I just described is an experimental approach, right? You give the input, you observe the output based on the measurement. How about the mathematical approach? How can we construct a model of this system so we can solve mathematically without using an actual oscilloscope? Okay. So what do? You could use many things. You can use actually basically the principles of the KCL. Okay? So the Kirchhoff current law at here. So what that says is, okay, you have Vs equal to I, the current times L, and then plus the voltage, okay, across the capacitor. Okay? The capacitor here. Now there's a mixture of I and Vc here. So what we can do is we can to make it consistent, because we know that this current, right, is related to the capacitor, right, like this, as we learn in an individual component. So I'll replace the I like this. So Vs equal to C times dVc over dt and plus Vc. Okay. So now this time, I'll write it just slightly different. I'll move the derivative to the left side, and then leave the Vs, okay, on the right side. Oh, yeah. Where did R go? The RC, of course. Very good. Okay. Yeah. So now you have. This is what we call a first order differential equation. Essentially, it's the governing equation mathematical model for this RC circuit. So this one here is basically what we call it's a math model. Okay. In essence, it's a first order ODE. Okay. Yeah, we'll learn that after this one here. Okay. Yeah. So in this model here, you included both the input and the output. Okay. And you can actually solve this differential equation to give you a solution for the output. Then you don't have to do it every time experimentally. Okay? So that's a very simple example to construct a model for electrical circuit. Okay. Similarly, you can look at the RLC circuits. Okay. But let's look at the mechanical example. A mechanical example, I'll use mass spring damper. Basically, we're putting all these components together. Okay. All right, so let's say I have a mass attached to a spring and a damper, like this kind of structure. So one end is fixed and the other end is free. Right? So this sign here, it says fixed, and this side here says free. Okay. So the mass M is free to go and vertically. Okay. So what we do is, let's see, in this case, we do have an external force applied to the mass at here. Okay. So there is an external force F at here. So you can consider this external force as the input, the motion of the mass, so we'll denote that as X. So this will be the output. Right. So this will be the output. And this X as we did for individual model. So this x at here again, it's the displacement, okay, reference with respect to equilibrium. Okay. Yeah. So the next question is, how do we describe, how can we get a solution for the motion of this object M, right, based on this kind of a loading condition, right? So then what you do is you isolate this object M at here. Okay. First, draw free body diagram, and then we apply the Newton's second law. Okay. So this is M at here. Then we draw all of the external force on this M at here. And apparently you have F, okay, external force, that's pointing up. That's your, again, that's the reference direction for the external force. And now you draw the external force or restoring force. This is K, this is B. The restoring force from the spring K. Restoring force is always in the opposite direction of the X. So which direction should I draw the restoring force? Downwards. The magnitude of the restoring force is K times X. The damper will also provide a restoring force, and this restoring force is also in the opposite direction of the displacement. Not displacement, the what? Velocity, right? So you draw it downwards, and this time it's B times X dot. Okay. So those are all the external forces at here. So once you have 1, 2, 3, all the external forces sketched as the free body diagram, right? This is your free body diagram here. Then you apply the Newton's second law, just like you apply that KCL over there for electrical circuits. Okay. Newton's second law says the total amount of force, right, equal to the mass times acceleration. Okay. So what we do is your total amount of force equal to m times x double dot. Okay, that's acceleration. So what is the total amount of force? So mx double dot equal to the total amount of force. Look at the free body diagram. You have a force pointing up, so that's positive. You have two forces going down, so you minus this x minus this bx dot, and that's the total amount of force by incorporating the direction, okay, into the equation. And then we can move all of the x to one side, so we get mx double dot, plus bx dot plus kx equal to the force F. Okay. That's it. That is the mass spring damper equation. That's the differential equation, or that's the math model describing this mechanical system here, simple mechanical system. And you can, if you feel comfortable to write the D, that's okay. It's the same thing. Okay. And this is a second order differential equation. Okay. And we can also solve this one. We'll learn how to solve this. The solution of this will give us, so this is your input, right? And then x at here is the output. So we'll be able to solve for x, and we'll see what x looks like, and then we'll be able to predict or describe the motion of the object M. Okay? Yeah. Any questions so far? Okay. Okay. Yes.
Why is kx being the output?
Not a key x. I mean, x is the output. Yes. Yeah. So you will be able to get a solution for x. Right. So m, b, k. Those are what we call system parameters. Right. This is part of the system. Yeah. Okay. Very good. So you actually probably should ask a question, which is over here, right? Where is gravity force? Okay. Why aren't we taking gravity force into this picture? Okay. The answer is here. Because we defined x as the displacement with respect to equilibrium. So what does equilibrium mean? Right? Equilibrium means you leave the mass and you let it settle. That's equilibrium, right? So if you initially let it go, for sure, due to the gravity, it will settle a little bit, but it will settle, right? It will settle at a certain equilibrium because it's basically static. Okay? And that's what this x here is defined. And because of that, we actually don't need to take the gravity force into the free body diagram. Okay? So in the lecture, I do have a very simple proof to show you why. I'm not sure I really want to do this, actually. I think you can take a look at that yourself, okay? Okay, it's a very simple explanation. As long as you define your displacement is from the equilibrium location, then we don't have to include gravity. Basically, it's cancelled out, okay, into the free body diagram. Okay, so take a look at that short half page of demonstration of why. Okay. Okay, so this is a simple case study here, right? So I'll show you a little more complicated case. Okay, we might not be able to finish this, but let's just draw it down first. Okay, this is a mass damper system again, but involve two masses. Here is a spring with stiffness K1. Here is a damper with damping constant B1. Here's the second spring with a spring stiffness K2. And there is external force applied, okay, as this. And we will denote each one of the mass, M1, M2, having a displacement x1 and x2. And this time we draw our arrow downwards, so we're treating downwards as a positive reference direction. Okay. So the question here is, what will be a mathematical model for this whole system in here, right? Okay, so before we jump into the rest of things here, let's do a generic. What is the difference between this system and the previous system? Two masses. In more mathematical term, the previous system has only one displacement, right, variable, and this one has two. So I could say the previous system has 1 degree of freedom, and this system has 2 degrees of freedom. Okay? Yeah. Then if previous system comes up with 1 differential equation, then this system, I guess I'm supposed to get what? 2 differential equations. Okay? Yeah. Second of all, okay, just think about a general situation. What do you envision that this kind of a system will draw here or here? Where do you envision that you could use it to model an actual situation? Because you don't do things just arbitrarily, right? And this system must be able to actually describe certain real situation. This is a mass spring damper system. This can be a very simple representation of what? Of the car suspension system, right? So your car has a spring, has a damper. This is the body, the total mass of the car, and that could be a very simple representation. And if you feel like your car is actually much more complicated, maybe this is the system. Who knows, right? Yeah. But that's the point. So whatever we're doing here, actually quite closely related to constructing an actual model of the system. Okay. So we'll look at the solution for this one in the next lecture. Okay? Yeah. Any questions? Okay.